Hey, welcome to NASA Edge.
An inside and outside look
at all things NASA.
Oh, that's going to leave a mark.
Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're here at Ball Aerospace in Boulder, Colorado.
To learn about STORRM.
The genetically gifted member of the X-Men?
No, not the role played by Halle Berry, but something a little more interesting. Let's take a look.
So, a sequel.
She's not in the sequel or an actual X-Men, but Amanda has joined us as a NASA Edge field reporter.
So what exactly is STORRM? Kind of what does it stand for, and what's kind of the big picture of what's going on?
Well, STORRM is an Orion-sponsored activity, and it's the sensor test for the Orion RelNAv Risk Mitigation. And it's an experiment that has been set up to help mitigate some of the risks that the Orion project level are carrying. Historically, relative navigation sensors have experienced failures on their first use in spaceflight. So with this concern, the Orion program is invested in this experiment to see if we can try to alleviate some of those issues.
We're going to be flying some relative navigation sensors that are cutting-edge technology, never been flown in space before, and we wanted to take the opportunity to get these on the shuttle before the shuttle stopped flying. So we accelerated the development of these sensors, and we're going to fly them on the shuttle on STS-134 and get this good data so that we can be ready to fly them on Orion.
STORRM has 4 key components. They consist of the sensor suite, which is the vision navigation sensor and the docking camera, and those are built at Ball Aerospace Technology.
There's a lot of different things that the astronauts want to be sure that they understand as they're coming in to dock.
They're very needy that way.
Yeah, I know. They want to see where they're going. It's such a hassle. So
Pilots.
I know, geez. So what the docking camera does, it's actually located on the docking hatch at the center line, so it provides the astronauts with a real-time view of the docking target and the docking mechanism as they're moving in. Since they're sitting on Orion sort of up and to the side, they don't have a real true line of sight to the docking mechanism itself, and so the camera provides their eyes.
We also have an avionics assembly that was designed and developed here at Langley, and that consists of the power distribution unit, the data recorder, and the data storage capability. One of the major challenges that we had on the STORRM project was how were we going to handle the high data rates and the significant amount of data that the sensors put out. We're talking in upwards of 1 terabyte of data for this project, and the shuttle infrastructure does not support this kind of data collection. So Langley Research Center had to develop a memory solution to support the project, and they ended up coming up with a design that can handle the terabyte, and it's also spaceflight quality.
So why couldn't you use like a terabyte drive from someplace like Best Buy?
The challenge that we have is that most of those commercial off-the-shelf products don't function in the space environment. We did some independent testing on these devices and found that they did not work for our application. So the Langley engineers had to design a radiation-tolerant memory device for this particular project. We also designed and developed here at Langley the reflective elements, which are the tracking features that the VNS will use during the experiment.
What got installed on the space station is some special targets that they were added to the space station, and they basically work like bicycle reflectors. And so there are spots on the docking target, and when the flash LiDAR illuminates those reflectors light up more brightly. And so then software that processes the data can identify those spots, and then by seeing those spots you can figure out which way you're rotated with respect to the space station and what all the angles are, so you can actually figure out exactly how you're sitting compared to where the space station is.
So tell me the difference between the VNS and the current system used for docking with the space station.
Yeah, so the space shuttle uses a scanning LiDAR system, which is basically has a little pencil beam light of a laser, and it goes and scans around the whole field of view and builds up an image over a short period of time. Now the VNS is a flash LiDAR, So the laser light comes out and goes through some special optics, and it illuminates the whole field of view. So it's just like a digital camera. You push a button, your flash bulb goes off, and you capture the whole scene in one single flash.
Langley also developed a STORRM software application, and that provides the experiment command control and monitoring while we're on orbit.
And basically the navigation data is one of the key components that go into those computers to tell the vehicle exactly where it's at. And this is really relative navigation. So this tells the vehicle where it's at with respect to whatever target it's flying to. In the case for STORRM, it's a relationship between the orbiter and the space station. It's very different than on the ground where you're trying to maybe approach something that's standing still. Of course, the space station is flying at 18,000 miles an hour. And we're coming in at the same speed, and we've got to try to meet it up exactly with no room for error.
Howard, we've talked about the camera and the VNS and the guidance and navigation, but there's some real other important elements to NASA STORRM too. Could you talk about those?
In addition, the shuttle program is really helping us out by flying unique rendezvous profile after they undock. So normally they'll do a trajectory in terms of approaching the space station like they normally do. So we'll get data on that flight.
And you'll be testing this for the first time during that part.
Right. Okay. And then we'll dock with the space station. They'll do the normal payload transfer and things like that. And then we'll have
mission stuff.
Okay. And then we'll have an opportunity to undock and fly a Orion-like trajectory.
So different than a shuttle approach.
Yeah.
But the procedures, obviously we want commonality in the procedures. So a lot of these things are done very similar to what we've always done before. They're just done at different times and different size burns. And the sensors we use at different times might be different.
So you can't get comfortable?
No, you can get comfortable at times. You're just going to be aware of what you're doing and how risky it is. But, with all the training that we go through to get ready for these things, you should be at a point where you're pretty comfortable.
Yeah, I'm just thinking that I'm probably, with the way you've explained it, I probably still have no shot at ever becoming an astronaut.
Sure you do. Send in the application.
There you heard it here first.
So can you talk about kind of what it means to be able to actually fly this on a shuttle mission and get a test like this?
So this is a very, very exciting opportunity for a program to get an opportunity to fly an experiment, especially on the space shuttle at this point in the program. The benefits of doing that is it allows us to get real spaceflight experience and knowledge on how the sensors are going to perform in their true environment.
The more exposure we get to the actual hardware and software, especially for STORRM, because there's going to be some interaction between the ground team and the crew on board, the more we know and understand the system, the much more successful we'll be, especially if there's any anomalies or issues arise and we've got to work through it to resolve them and still meet our objectives.
My job is to watch the performance of the hardware, the laptop computer interface, and report to Mission Control what I'm seeing to allow them to acquire the data they need to ultimately calibrate that system and make it useful for an Orion.
So you're like the human component. You'll give them real feedback from an astronaut perspective, and they'll compare it with the science.
Right. Unfortunately, I'm the human in the loop, which isn't always a positive thing. Well, you never know how that's going to end up.
So you're almost like the goofy co-host of STS-134.
Okay.
So today was Drew's first chance with the real flight hardware. You can see real images, and we had no time today where we had to say, this is just a function of anything. This is what you are going to see on orbit.
In the simulations we've done previously, it's sort of been make-believe, and they'll tell me what I'm supposed to see, and then I'll imagine I'm seeing that and report back to them what it is they told me I should be seeing. This time we actually saw the data, and I was able to work through the procedures and also give them feedback as to whether or not I understand the procedures, and also whether I feel that somebody else running the procedure, if it's not me, could also perform those tasks without having the knowledge that I have.
Do you have a backup for STS-134 if you decide you can't handle the task of...
The backup is anybody else who's breathing and close to the system if I'm not.
Okay, I'm everything but close to the system. Was he like that?
You're always trying to be an astronaut. Maybe I should come on your show and be like a host.
And I'd be jobless. All right, it's nice talking to you again, Drew. Appreciate it. No, this is great. Awesome.
Thanks, everybody.
You've been watching NASA Edge, and look at everything inside and outside of NASA. Oh, that's not it, is it? What is it? Is it inside? What is it? What is it?
Inside and outside.
It's inside and outside. Look. Oh, so it's. You're welcome. You are watching. You're watching NASA. an inside and outside look at everything NASA.
All things.
See, it's the all things now. You are watching NASA Edge, an inside and outline, an inside.
One more time.
No, I can't do it.
One that works.
Good luck. You're watching NASA Edge, an inside and outside look of all, an inside and outside look at all NASA. All things. I probably should have watched your show, Blair.